Okay, so here's the proof for lemma 1. So we've got, we start by fixing a basis, B. So we've got this basis. And we're going to suppose that we have a representation for each vector V, right? So we've got a representation with respect to the basis B for V1 all the way to some V sub k. So we've got all these representations. So here are the coefficients. Such that, so again, part of this supposition here, so you have these representations such that V1 equals the linear combination of the coefficient vectors here in this representation here and the basis, and so on, all the way through here. So all these representations, we can write each vector V1 through V sub k as this linear combination. Okay? Then, what happens? We know we have, then this linear combination equals the zero vector. Okay, so linear combination of a sub 1 times v sub 1 all the way through a sub n times v sub k is equal to the zero vector is equivalent to these. Okay, so all we're going to do is now, since we know that each vector can be represented as this linear combination, we're just going to substitute. So now we just write the zero vector as a sub 1 times this linear combination plus all the way to a sub k times this linear combination. And the cool thing is now when you distribute the a's, right, the a sub 1 through a sub k, and then you could use the properties of commutativity, right? You can just regroup everything, and now you can take and factor out all the betas. So then it becomes the linear combination of these coefficients, right? A1 times C11 plus all the way to A sub k times C sub 1k times this quantity times beta 1 plus all the way to this one here. Okay, now, so this is equal to the zero vector. Now that is equivalent to, well, these are equivalent. Okay, so now, okay, so we look at this and we see that the zero vector here is just a linear combination of the betas, right, from the basis. And so obviously that equation is going to be true if the coefficients are zero, right, because this is a basis. And what's one of the properties from the definition of a basis? They're linearly independent. So that would mean all of these coefficients would have to be equal to zero. Okay, now, in the previous theorems that we studied, says that this is going to be true if and only if the coefficients are zero, right, as we just mentioned. So the relationship is going to be equivalent to this. Okay? Here's what we're going to have to write. So if all the coefficients are going to be zero, now we set this up. So this means that A1 C11 plus all the way to plus A sub k C1k is equal to 0. All the way to what? A1 Cn1 plus all the way to A sub k Cnk is equal to 0. Okay? So now, this gives us an equivalent recast Okay, so we can rewrite this. In fact, let me erase this, so you guys should have this part. So I'm just gonna erase everything up to here. Okay, so now we've got this. Let's rewrite this as let's see here. Well, yeah. So here are the A's. So we can rewrite this as A1 times the column vector C11 all the way to CN1 plus dot 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 plus, and then we A sub k times C sub 1k all the way to C sub nk is equal to the zero vector. Now, take a look at this. This not only does a relationship hold for one set, if it holds for the other, but it is the same relationship. All the A sub i's are the same. And that's the end of the proof. Because remember, what were we setting out to prove? Right? It says where B is a basis with n elements for any set of vectors A1, V1 plus all the way through AK, VK equals the zero vector with respect to the V's, if and only if A1 times the representation of V1 equals the zero vector in N, which is exactly what we did. So we showed a whole bunch of equivalences starting with the linear combination of the V vectors all the way to here, and so that finishes the proof.